And today we're going to continue our discussion of elementary number theory and methods of proof. Direct proof and counterexample with divisibility. When you were first introduced to the concept of division in elementary school, you were taught that 12 divided by 3 is 4, because if you separate 12 objects into groups of 3, you get 4 groups with nothing left over. This also might have been described as 12 is evenly divisible by 3, or 3 divides 12 evenly. Number theory is termed as being beautiful in this slide here. The notion of divisibility is central to the concept of number theory. If n and d are integers, then n is divisible by d if and only if n equals d times some integer and d does not equal 0. Instead of n is divisible by d, we can say n is a multiple of d, d is a factor of n, d is a divisor of n, d divides n. The notation d vertical line n reads n, d divides n. Symbolically, that means that if d divides n, or if d divides n, if and only if there exists an integer k such that n equals d times k and d does not equal 0. The vertical line with a slash through it is read d does not divide n. Simple math here. Yeah. Yes. Yeah, all yeses on this one. Basic math. Take you back to, what, maybe 4th grade? But yeah, negative numbers can be factors of numbers as well. If k is any non-zero integer, does k divide 0? Yeah, because 0 times k is 0, so yes, 0 times k is 0, so k divides 0. Two useful properties of divisibility are, one, that if one positive integer divides the second positive integer, then the first is less than or equal to the second, and that the only two divisors of 1 are 1 and minus 1, negative 1. If a and b are integers, is 3a plus 3b divisible by 3? If a and b are integers? Yeah, because you can divide out the b, a plus b is an integer, so it would be, you could factor out the 3 and have 3 times the quantity a plus b. If k and m are integers, is 10 km divisible by 5? Yeah, because it would be 2 km if you divide it by 5. So yeah, distributive law and associative law of algebra. When the definition of divides is rewritten formally using the existential quantifier, the result is this here. Since the negation of an existential statement is universal, it follows that d does not divide n if and only if, for all integers k, n does not equal k dk or d equals 0. In other words, the quotient n divided by d is not an integer. So that would be the negation of that for the definition of not divisible. 4 does 4 divide 15? No, because it's yeah, you have a remainder of 3.75, which is not an integer. Yeah, 3.75. Alternate way to define a prime number is to say that an integer n greater than 1 is prime if and only if its only positive integer divisors are 1 and itself. Proving properties of divisibility. Prove that for all integers a, b, and c, if a divides b and b divides c, then a divides c. This is the transitivity of divisibility. Since the statement to be proved is already written formally, you can immediately pick out the starting point, and the conclusion must be shown. Starting point, suppose a and b and c are particular but arbitrarily chosen integers such that a divides b and b divides c. Show that a divides c. In other words, c equals a times some integer. A times some integer. Since a divides b, b equals ar for some integer r. Since b divides c, c equals b times s for some integer s. C then is equal to b times s. Substitute ar for b, and you get c equals ars. Ar times s. By the associative law, you can change the parentheses to be a times quantity rs, and because r and s are integers, this is an integer, so c equals a times some integer. So for theorem 443, for all integers a, b, and c, if a divides b and b divides c, then a divides c. Divisibility by a prime. Any integer n greater than 1 is divisible by a prime number. Any integer, whether it's itself or something else, or some other value. Counterexamples and divisibility. Is the following statement true or false? For all integers a and b, if a divides b and b divides a, then a equals b. Is that true or false? Not sure, huh? Well, let's see here. Statement is false. Counterexample. This discussion describes a mental process that may just take a few seconds. It's helpful to use it consciously, however, to solve more difficult problems. To discover the truth or falsity of a statement such as the one given above, start off much as you would if you were trying to prove it. So suppose A and B are integers such that A divides B and B divides A. Must it follow that A equals B, or could it happen that A does not equal B for some A and B? Focus on the supposition. What does it mean? So that starting point, B would mean that B equals H at A and A equals KB for some integers H and K. Must it follow that A equals B, or can you find integers A and B that satisfies these equations for which A does not equal B? The equations imply that B equals HA, H equals KB, so H times K equals B, and B does not equal to 0. Since B divides A, B does not equal to 0. And so you can cancel B from the extreme left and right sides and obtain 1 equals HK. In other words, H and K are divisors of 1. But by theorem 442, the only divisors of 1 are 1 and minus 1. Thus, H and K are both 1 or both minus 1. If H and K are equal to 1, then B does equal A. If H and K equal minus 1, then B equals minus A. And so A does not equal B. Showing the falsity of the statement. This suggests that you can find a counterexample by taking B equals minus A. Here is a formal answer. The supposition, counterexample of 2 and minus 2, and the conclusion. All right. Unique factorization of integers theorem. The most comprehensive statement about divisibility of integers is contained in the unique factorization of integers theorem. This is also called the fundamental theorem of arithmetic. Unique factorization of integers theorem says that any integer greater than 1 either is prime or can be written as a product of prime numbers in a way that is unique, except for perhaps for the order in which the primes are written. For example, 72 equals 2 times 2 times 2 times 3 times 3. Or other ways of writing it with the primes in different order. The 3 2's and the 2 3's may be written in any order, but any factorization of 72 is a product of primes. As a product of primes, must contain exactly 3 2's and 2 3's. No other collection of prime numbers multiplies out to be 72. Unique factorization of integers theorem. Given for any integer n greater than 1, there exists a positive integer k, distinct prime numbers p1, p2, p3, etc. to pk, and positive integers e1, e2 to ek, such that n equals p1 to the e1 power times p2 to the e2 power etc. to pk to the ek power. And any other expression for n as a product of prime numbers is identical to this, except for perhaps the order in which the factors are written. Definition. The standard factored form of n is an expression of the form given here, where k is a positive integer, primes are the base is are the prime numbers, and e are the powers, and the powers are, or the bases are written in ascending order. Write 3,300 in standard factored form. No? Divide by 3, make it 1,100. How about we do this? Divide it by 100, which is 10 times 10, which is 5 times 5 times 2 times 2, and 33. 3 is 3 times 33 is 3 times 11, so it would be 2 times 2 times 3 times 5 times 5 times 11, right? That sound right? Sounds right. All right. Well, with a 2 to the power of 2, 3 to the power of 1, 5 to the power of 2, 11 to the power of 1 in standard form. All right. Suppose m is an integer such that 8 times 4, 7 times 6 times 5 times 4 times 3 times 2 times n equals 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10. Does 17 divide m?
Yes.
Okay. So this is going to be a lot of 2s. You can cancel out the. Let me see if I can do this on the board here. The 16 is taken care of by the 8 and the 2. The well, well, this is some integer because it's a product of integers, right? This is some integer. So some integer. Yeah, you'd have to divide this side. Let's see here. That's 10. And 2 and 6. Get rid of the 12. 12.
14.
14 is 2, and this is 7. And 5, and gets rid of the 3. So yeah, these cancel out to 1. So m equals 17 times some integer. So yes, 17 does divide m. Since 17 is one of the prime factors of the right-hand side of the equation, it is also a prime factor of the left-hand side by the unique factorization of integers theorem. 17 does not equal any prime factor of 8, 7, 6, 5, 4, 3, 2, or 2 because it is too large. Hence, 17 must occur as one of the prime factors of m. That's the shortcut way of doing it. I hadn't gotten as far as reviewing the slides, so I didn't get the shortcut. But yeah, I think that's it for this slide deck. Go to file there. F4. Okay. Okay. How many slides do we have? I might be able to get 3 in today. All right. Elementary number theory and methods of proof. Part 5. Division into cases and the quotient remainder theorem. The quotient remainder theorem. Given any integer n and positive integer d, there exist unique integers q and r such that n equals dq plus r. And r is less than or greater than or equal to 0, but less than d. If n is positive, the quotient remainder theorem can be illustrated on the number line like so. R is the remainder, q is the quotient, d is the divisor, and n is the original number.
And the original number R.
R is the remainder of division of n by d. If n is negative, the picture changes. Since n equals dq plus r, where r is non-negative, d must be multiplied by a negative integer q to bring dq either exactly to n or to a point below n, in which case the positive integer r is added back to dq plus r to back up to n. All right. For each of the following values of n and d, find integers q and r such that n equals dq plus r. N equals 54, d equals 4. So that would be 13 and 2. Is that right? 54 divided by 4. Is 13 with a remainder of 2. Sound about right?
13.5.
Yeah, so 13 with a remainder of 2. So Q would be 13 and R would be 2. N equals 54. D equals 70. Be 0 with a remainder of 54. Minus 1 with a remainder of, no. 0. 0 with a remainder of 54. Q would be 0 and R would be 54, right? For C? Because D is greater than N? I think that's right. Yeah, Q is 0 and R is 54. Yeah. Div and mod. These functions can be found in computer languages when dealing with integers. Given an integer n and a positive integer d, n div d is the integer quotient obtained when n is divided by d. N mod d is the non-negative integer remainder obtained when n is divided by d. Symbolically, if n and d are integers and d is greater than 0, then n div d equals q and n mod d equals r, if and only if n equals dq plus r, where q and r are integers and r is greater than or equal to 0 and less than d. (32) div 9. How would C++ do this with integer math? (32) div 9. What's 32 divided by 9? 3. It would be 3. It would be the integer quotient. C++ and many other languages, when you're dividing integers, it gives you an integer quotient. It doesn't give you 3 point. Yeah, because you're using 2 integers. 32 mod 9 would be the remainder. So what's 27 minus 32 minus 27? 5. So it'd be 3 and 5. Yeah. There you go. It says use a 4-function calculator to compute it, but to compute n mod d, substitute n div d in the place of q and n mod d in the place of r in the equation n equals dq plus r. The result is this here. Solving for n mod d equals n minus d times n div d. Thus, when you use a 4-function calculator to divide 32 by 9, you obtain the expression like 3.5555, etc. Discarding the fractional part gives you 3. So 32 equals 9 times 32 div 9. which is 27. Therefore, it equals 5. Prove that if n is a positive integer, then n mod 10 is the digit in the ones place in the decimal representation for n. How'd you go about proving that? Well, are the lights getting dimmer? Proof. Suppose n is any positive integer. Decimal representation for n is d sub k times d sub k minus 1 times d sub k minus 2, etc. to d minus 2, or d sub 2 to d times d sub 1 times d sub 0, where d0, 1, 2, 3 to k are integers from 0 to 9 inclusive, and d sub k is not equal to 0 unless n equals 0 and k equals 0. So n equals this expression here, which you might recognize from the number system section of digital logic, if you've taken digital logic already, where the digits are multiplied by the powers of 10. So factoring out the 10 from all the all but the final term gives 10 times this mishmash here. Thus, n equals 10 times some integer plus d sub 0. And so n mod 10 equals d sub 0, which is the digit in the ones place in the decimal representation for n. We didn't look at that one. Representations of integers. We defined an even integer to have the form twice some integer. At that time, we could have defined an odd integer to be one that is not even. Note, the fact that any integer is either even or odd is called the parity property. Prove that given any two consecutive integers, one is even and the other is odd. Two integers are called consecutive if and only if one is one more than the other. So if one integer is m, the next consecutive integer is m plus 1. To prove the given statement, you can divide the analysis into two cases. Case 1, where the smaller of the two integers is even, and case 2, where the smaller of the two integers is odd. Case 1, m equals 2k for some integer k, and so m1 equals 2k plus 1. m plus 1 equals 2k plus 1 for the second, which is odd by the definition of odd. So in this case, one of m and m plus 1 is even and the other is odd. Case 2 is the same type of thing, with a little bit of the distributive law in there. So therefore, m plus 1 equals twice some integer, and m plus 1 is even. Hence, also one of m and m plus 1 is even, and the other is odd. It follows that regardless of which case actually occurs for the particular m and m plus 1 that are chosen, one of m and m plus 1 is even and the other is odd. The parity property. Any two consecutive integers have opposite parity. Is it odd or even parity? You run into parity also in communications. You send a sequence of bits, and with even or odd parity, you send a parity bit to make the number of bits sent either even or odd, depending on the parity that you agree to use. So adding 1 either makes it an even number, or adding 1 makes it an odd number. Method of proof by division into cases. To prove a statement of the form if A or A1 or A2 or A3 or AN, then C, prove all of the following. If A1, then C. If A2, then C. Yada, 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 to if AN, then C. This process shows that C is true regardless of which of A1, A2, or AN happens to be the case. Show that any integer can be written in one of the 4 forms. N equals 4q, n equals 4q plus 1, or n equals 4q plus 2, or n equals 4q plus 3 for some integer q. Well, you would apply the quotient remainder theorem with a divisor equal to 4. This implies there exists an integer quotient q and a remainder r such that n equals 4q plus r. And r is greater than or equal to 0 and less than 4. But the only non-negative integers of r in this that are less than 4 are 0, 1, 2, and 3. Hence, all of these cases, for some integer q, n mod 4 equals 0, 1, 2, or 3. Prove the square of any odd integer has the form 8m plus 1 for some integer m. Any ideas on how that might be approached? Well, checking some examples should convince you that the statement may be true. Begin to develop a proof by asking, where am I starting from? What do I need to show? To help answer these questions, introduce variables to write the statements more formally. Formal restatement. For all odd integers n, there exists an integer m such that n squared equals 8m plus 1. From this, you can immediately identify the starting point and what is to be shown. Show there exists an integer m such that n squared equals 8m plus 1. Why should there be an integer with that property? That would say that n squared minus 1 over 8 is an integer, or that 8 divides n squared minus 1. Perhaps you could use the fact that n squared minus 1 equals n minus 1 times this quantity n plus 1. Does 8 divide n plus 1 times n minus 1? Well, since n is odd, both n minus 1 and n plus 1 are even. That means their product is divisible by 4. That's not enough. You need to show that the product is divisible by 8. You could also try another approach by arguing that since n is odd, you can represent it as 2q plus 1 for some integer q. Then n squared equals 2q plus 1 squared, which equals 4q squared plus 4q plus 1, which is 4q squared plus q plus 1. It's clear from this analysis that n squared can be written in the form of 4m plus 1, but may not be clear that it can be written as 8m plus 1. Yet another possibility is to use the result of example 456. That example showed that any integer can be written in the form of 4q or 4q plus 1 or 4q plus 2 or 4q plus 3. Two of these, 4q plus 1 and 4q plus 3, are odd. Thus, any odd integer can be written in the form of 4q plus 1 or 4q plus 3 for some integer q. You could try breaking into cases based on these two different forms. It is true that the square of any odd integer has the form of 8m plus 1. I would suggest you work out the proof yourself, as this proof might be showing up on a quiz or a test in the near future. So it gave you 3 starting points. You can review the slides to get the slides are all on Canvas, so you can get the gist of what's going on and the 3 different starting points it gave. Absolute value and the triangle inequality. The triangle inequality is one of the most important results involving absolute value. It has applications in many areas of mathematics. For any real number x, the absolute value of x, denoted by x between 2 vertical bars, is defined as follows. X if x is greater than or equal to 0, or minus x if x is less than 0. Lemma 454. For every real number r is less than or greater than or equal to the negative of the absolute value of r, and less than or equal to the absolute value of r. For every real number r, the absolute value of negative r is equal to the absolute value of r. So the triangle inequality is, for all real numbers x and y, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. And that is it for this slide, Brett. That was 5, 6. Let's see if we can get through 6 before the end of the class session. How many slides we got here? Oh yeah, we got this. Okay. Section 4.6, direct proof and counterexample, floor and ceiling. These are functions you find in the math libraries of most languages. Imagine a real number sitting on a number line. The floor and ceiling of the number are the integers to the immediate left and to the immediate right of the number. Unless the number is an integer, in which case its floor and ceiling are both equal to the number itself. They have built-in function, many computer languages, like I said, have built-in functions that compute these values automatically. Like I said, they're typically in math libraries. But floor and ceil, C-E-I-L, I believe, is the typical abbreviation for those functions. Okay, given any real number x, the floor of x denoted by this, let me write it a little bit bigger so you can see. It's the kind of brackets with the x in the middle there. That's for the floor. The floor of x, denoted by x, denoted by this symbol, is defined as that unique integer n such that n is less than or equal to x, and x is less than n plus 1. So, yeah. The floor of x is n if and only if n is less than or equal to x, and x is less than n plus 1. So, likewise, the floor or the ceiling is denoted with the that kind of symbol. That it's x. The ceiling of x is that unique integer n such that n minus 1 is less than x, which is less than or equal to n. So it's the next integer up for a real number, unless the number is an integer. Compute the floor and ceiling for each of the following values of x. A, 25 divided by 4. 25 divided by 4, what's the floor and the ceiling? And the ceiling value?
What is the ceiling denoted by?
It's the it's that's the symbolic representation of ceiling of x. Seven. There we go. B, floor and ceiling. No calculation really needed there for that. The ceiling would be 1. Floor would be 0. Now this one's a little bit trickier. Floor and ceiling of C. What would the floor be?
-2.
Mm-hmm. No.
-3.
-3. It's the next integer down. It's the next integer down. And the ceiling would be -2. Because that would be the next integer up on the number line. So, yeah. So, an application. The 1,370 students at a college are given an opportunity to take buses to an out-of-town event. Each bus holds a maximum of 40 passengers. For reasons of economy, the leader of the event will send only full buses. What's the maximum number of buses the event leader will send? The floor or the ceiling of that? The floor, because he only wants to send full buses. So the divided by 40 and the remainder would be left on campus. Is that 1370? Yeah, 34 buses. If he is willing to send one partially filled bus, it would need to be allowed to allow all the students to take the trip would be 35. Is the following statement true or false? For all real numbers x and y, the floor of x plus y is equal to the floor of x plus the floor of y. I hear false and true. False, why? Can you give me a counterexample? If let's do this out on the board here. If x equals 2 and y equals minus 2.5, the floor, I don't know if this is going to work out or not as a counterexample. I just picked two numbers. X plus y, the floor of that would be it would be -1. You see how I got that? So 2 minus 2.5 is minus 0.5, and the floor of that is -1. No, this would maybe, and then it would be 2 minus 3. Yeah, that would be -1. So that wouldn't be a good counterexample. I remember this as being false. I just don't remember the counterexample that it was given in the, haven't done the spoiler for it yet. Oh, they do 1/2. Okay. Yeah, the statement is false. Counterexample could take x equals y equals 1/2. The floor of each of those would be 0 plus 0. X plus y would be 1. And the floor of 1 is 1. So that it is not always the case that the floor of x plus y equals the floor of x plus the floor of y. To arrive at this counterexample, you could have reasoned that suppose x and y are real numbers. Must it necessarily be the case that x plus y imagine the various quantities can take? And it goes into the fractional parts and all that sort of stuff. But yeah, it's fractions, yeah. Yeah, if the fractional parts are greater than, if the sum of the fractional parts is greater than or equal to 1, then it doesn't apply. So if x is the fractional part is 1/2 and y is the fractional part half is 1/2, then the sum is equal to 1, thereby throwing off the calculation. Prove that for every real number x and for every integer m, the floor of x plus m equals the floor of x plus m. Well, begins by supposing x is a particular but arbitrarily chosen real number and m is a particular but arbitrarily chosen integer. Since the equation involving the floor of x and floor of x plus m is reasonable, it is reasonable that one of these quantities give one of these quantities a name. By definition of floor, n is an integer, and n is less than or equal to x and less than n plus 1. This double inequality enables you to compute the value of x plus m, floor, in terms of n by adding m to all sides. Thus, the left-hand side of the equation to be shown is n plus m x since the right hand of the equation, floor of x plus n equals n plus m. Thus, the floor of x plus m equals the floor of x plus m. It's not very clear when I say it, but when you read it, it makes a little bit more sense. So I get the symbols mixed up in how I express it verbally. All right, this discussion is summarized as follows. For every real number x and every integer m, the floor of the quantity x plus m equals the floor of x plus m. And for any integer n, the floor of n divided by 2 is n if n divided by 2 if n is even, and n minus 1 divided by 2 if n is odd. Given any integer n and any positive integer d, the quotient remainder theorem guarantees the existence of a unique integers q and r such that n equals dq plus r. The following theorem states that the floor notation can be used to describe q and r as follows. Q is the floor of n divided by d, and r is equal to n minus d times the floor of n divided by d. Thus, if on a calculator or in a computer language, floor is built in, but div and mod are not, div and mod can be defined as follows. For a non-negative integer n and a positive integer d, n div d equals floor of n divided by d, and n mod d equals n mod d equals n minus d times floor of n divided by d. Note that d divides n if and only if n mod d equals 0. In floor notation, this means that d divides n if and only if n equals d times the floor of n divided by d. If n is any integer and d is a positive integer, and if q is equal to n divided by d floored, then and r is equal to n minus d times the floor of n divided by d, then n equals dq plus r, and r is greater than or equal to 0 and less than d. Use floor notation to calculate or to compute 3850 div 17 and 3850 mod 17. Yeah. By formula 461, it works out to be the sequence of calculations. And so you get 226 and 8. And that is it for the slide deck. Okay. I guess we can call that a day. Covered 3 sections today. More on number theory and various types of proofs. Keep in mind that proof in there on, was it section 4.5? That might be coming up on a coming quiz or test. So keep that in mind. Work on. Either next Thursday or the following Tuesday will be the next test or quiz. So have a good day.